Yes.
Okay, this is the review from 4.1. So in the first, you have to figure out which of those graphs match this. So we all know that exponential 3 to the positive x looks like this, yes? So what does the negative do with the x? It flips it this way, right? Okay, and then what does the minus 2 do?
To the right.
Down 2, right? So which graph am I?
You are. Yep.
Top right one, right? So you have to be able to list transformations like that and apply them on a graph. All right, second part here. Write an exponential function that has the condition of initial value of 16 and it decreases at a rate of 18% per month. So if you're increasing or decreasing at a rate per time period, you're going to do this formula here. Just your basic exponential, a, b to the x. But keep in mind, the b here, if you're increasing, it's going to be 100 plus that rate. If you're decreasing, it's going to be 100 minus that rate. The b is your growth factor. Okay, it's not the percentage. So we're not going to put a 0.18 in there. We're going to do 100 minus 18% is what percent? 82%. So we're going to say y equals my initial value, which is 16 times 0.82 to the x. So your b factor should be the percentage that's left after the it's decreased happened. Okay? Pretty easy breezy. Now if it said continuous, that's when you use the per formula. And decreasing it would be negative. But it didn't say continuous. We're changing a certain percent per year. Per month in this case. Alright, 4.2 is on log functions. And we will buzz through as quick as we can learn. Okay, Math Excel due on Wednesday. So, the log function. I'm recording.
Oh, I thought it was fun.
I paused it during Logan's entrance because I knew that was going to take us a minute. Alright, so you have two forms. You have a logarithmic form and exponential form. I'm just going to skip to the next slide because we have somebody that will help us with this. Are you ready?
Yes. Yeah.
Ben the log bunny will help us with the forms. Alright? So when it's an exponential form, your base is the b, you have an exponent which is your e, and it equals a number. When you convert it to logarithmic form, it's log of the bunny. So the b becomes this lower case b, n to the e.
That's kind of evil.
It is.
I'm gonna lie, the rabbit's creeping me out.
He looks like the bunny on.
Bunny.
You remember the bunny on? Did you guys ever see? It's not Red Riding Hood, but you know what I'm talking about. Hoodwinked. Looks like the bunny on Hoodwinked, doesn't he, a little bit?
It looks like
The eyes.
yeah.
Okay, here we go. Did you write Ben the log bunny down? Because it will help you.
Bunny.
Could be. Ben the log bunny. We written this down. So, in logarithms, the b has to be greater than greater than 0. You can't have a negative b, and your b can't be 1. Okay. We ready? Here we go. So, in this form, this is Ben, and we want to write log bunny. So write it in log form. You've got to be able to convert from one form to the other form. So this one's kind of easy. Log, the base is 8. The number is this big long number, and it equals the exponent. Okay, try the next one. I know some of you have already done this homework, so. Log bunny. Base number equals the exponent, which is your e. If they are in log form, you have the bunny. Now write then base to the e equals n. Are we good? Do we understand how to rewrite back and forth?
Yes.
I'm going to write the next one real quick. All right. Here we go. We're going to solve these without our calculator. And I know it has that cute little log button in it that you might have used during your math Excel, which you won't be able to use.
That's how I did the whole thing.
I know. That's why you're done with it.
Yeah.
Because we didn't do it the way we're supposed to do it. Okay.
I can redo it.
All right.
He was just trying to be numbers.
Yes, I know. Here we go. We're going to write this. We don't know what it equals, so we're going to set it equal to x. And we want to write it exponentially. So 2 to what power gives me 8? The logs are just saying what's the exponent. Okay. So we can rewrite 8 as 2 to the third. And I'm kind of showing the reasons why here. If the bases are the same, then the exponents are the same. So yes, this equals 3. Easy breezy. Yes? Okay. So we're trying to get the bases to be the same. So in this next example, 3 to what power gives me the square root of 3? So how do I write the square root of 3 as a power of 3? 3 to the 1/2. So x equals 1/2. As soon as the bases are the same, we can set the exponents equal. Easy enough? Okay. 5 to what power gives me 1 over 25? How do I rewrite 1 over 25 as a power of 5? You can kind of do it in steps. 25 is 5 to the second. We're going to bring the 5 up. That makes the exponent negative. So x equals -2. So you understand how you have to be able to do these? Now, some of them, like the first one, I would not require any kind of work. I'd like to see, what you did. The first part, at least. This next one is a log property. Kind of always is. Doesn't matter what base it is. What exponent always changes it to a 1? 0. So that's a log property. Anytime you're taking the log of 1, regardless of the base, it can be base 4, base 10, base 306, it's going to be equal to 0. This is also a log property. What exponent do you put with 7 to get 7? 1. All right, I'm going to give you a little bit more challenging one. Ready? Okay, let's try this one. Okay, take a minute. Start it like we've been doing. Base to the x equals the number. Okay, did everyone start it that way? So 5 to the 1/3 is how I would write that. And it already had an x, so the x is still there next to it. Should multiply the exponents there. And on this side, I get 5 to the second. So our bases are the same. So what does x equal? 6. Because you're going to multiply both sides by 3 to get rid of that fraction. Okay, does that make sense? Nothing crazy? Easy breezy. We clicking? Try these without a calculator. This is going to equal 1, right? Anytime the base and this number are the same, it equals 1. 8 to the first power gives me an 8. What about this guy? 3 to what power gives me 3 to the 6? Yeah, that's going to equal 6, right? Over here, this is an exponential form. I'm going to write this a little bit bigger so you can kind of see what I'm talking about. This whole thing is the exponent. So we're in Ben form right now. So we want to write it logarithmically. So the log of the base n equals the exponent. What does the n equal? 11. They're the same on both sides. So n has to equal 11. Right? So those are log properties. Now, whether you memorize them or just write them exponentially and follow the rule, you're good to go. Okay? Good? Transforming log functions, guys. The transformations, again, are the same regardless of whether I'm talking quadratic, exponential, logarithmic. We're either in shift, left, right, up, down, stretch, shrink, flip, whatever. So what happens to the log graph? So this is your basic log graph. It comes up along the x-axis and swings, along the y-axis and swings over. Okay? So what's going to happen to that graph when I add 2 to the equation? It's going to go up 2. Right? You have to be able to describe that in words. And how about the one on the right there? Log of x minus 1 base 3. It's going to move to the right 1, right? Okay, the one down here on this bottom left, negative out front over the x. Good. Okay, and if you have a negative in with the x, it's a reflection again over the y in this case. Those transformations are the same no matter what function they're applied to. Okay? Easy enough? The only one that changed our vertical asymptote is the horizontal shift. The asymptote shifts with it. The one on the top right there. Okay? All right. We are buzzing along, guys. Logarithmics and exponentials are inverses of each other. Okay? So the log graph is in black. Tell me what the domain is. Where are the x values? 0 to positive infinity, right? Doesn't include 0. That's an asymptote. What's the range? Good. Negative infinity to positive infinity. Which spans the whole. Do we have an x-intercept? Does it cross the x-axis? Yes. 1. So the log of 1, 0. Yes? Okay. Does it have a y-intercept? Look at the black graph. Does it cross the y-axis? Okay. It has an asymptote, a vertical asymptote at x equals 0. In behavior, limit as x goes to infinity. What's the height of the graph? As x gets bigger and bigger and bigger, what's the height? What's the height approaching on the right side here? Infinity. It's very slow. Log functions rise very slowly, but it's still going to get to infinity eventually. Or try to get to infinity, I should say. Now, the left in behavior. Where is the x approaching but never going to hit? 0. So the left side of this graph's end behavior is going to be x going to 0. And what is the y going to? As x is going to 0, the y is going to negative infinity. Remember, it's approaching an asymptote, so it's going to be infinity or negative infinity. Okay? So again, if you have the graph, you should be able to state all the properties. And there's other things we're going to talk about. It's continuous, it's constantly increasing, that type of thing. It doesn't matter what base you have. This is base B. That could be a 3, that could be an E, that could be a 12, right? It could be any base. The common log is base 10. So when you look on your calculator, when it says log, that's this guy. That's the base your calculator has, base 10. I'm talking without your little baby button that you can push that shows you the log base and everything. So if it's base 10, we won't show a 10 here. It's like when I say, what's the square root of 16? You know that's the square root even though I don't put a 2 there, okay? When it just says, what's the log of whatever, you're not going to have a baby 10 there. I want you, without your calculator, to estimate what is the log of 2,381. So let's think about it. This is base 10. So 10 to the first power is 10, right? 10 to the second power is 100. 10 to the third power is 1,000. 10 to the fourth power is 10,000. Yes? Do you see that this number resides in between 1,000 and 10,000? So the log value has to be between 3 and 4. So this has got to be 3 point something. Does that make sense? Okay. But without your calculator, what's the log of 100? Ten to what power gives me 100? Okay, 10 to what power gives me the fourth root of 10? 1/4. 10 to what power gives me 1 over 1,000? So it's going to be -3, right? This is the same thing as 10 to the -3. So we only want the exponent as the answer. Okay, what's the power? Let's see if you can do this without too much work. This base and the base of that guy are the same, so what's this going to equal? Anyone memorize it from the other slide? I'm going to write it logarithmically. Log base 10 equal log base 10, so x equals 6. Okay. You don't have to memorize the properties. We can always just write them exponentially and figure it out. This is the natural log function. It's the same properties as the log base b that we talked about. Same thing. Same curve, same sketch of the graph, same everything. Okay? All right. Same properties as every other log. So the natural log of 1, oh, by the way, natural log, I'm sorry, I have no idea why on your calculator it's an ln and not an nl for natural log. I have no idea. Log and natural, I have no idea. Okay? But they won't, so if I say the natural log of 17, they won't put the e there. Natural logs are base e. You were to know that. Okay? So, same properties though. E to the 0 equals 1. E to the 1 equals e. So, you know, these properties are the same. It doesn't matter what base you're in. Okay? Log properties are the same. We're skipping. Here we go. Here, skip. So this is Benford's law. If you are looking at a big list of numbers, this example is actually in your book at the beginning of the chapter. So I am looking at this huge detecting possible fraud at all these numbers. And it says, listed below in 2 columns is the size in square kilometers of the first 50 countries in the world by alphabetical order. One column contains the real data, and the other column contains fictitious data. Can you guess which column contains the real data? If we use Benford's law, you have digits 1 to 9. You can't start a number with 0, correct? First digit can't be 0, because then you're down to the next digit. If you plug the number you want to talk about, so we're going to say the first digit is a 1. So we're going to put a 1 in our formula. What base are we in? It just says log 10. So if I plug a 1 in, we're base 10. What's the log of 1 no matter what base it is? Nope. What exponent do I put with something to get a 1? 0. So when you have the log of 1, you can just cancel that out. You're going to pick your calculator up. What is the log of 2? .301. So 30% of the numbers in a list of data that's generated should be a 1. So you can try it with a 2. So I put a 2 in there. So we're taking the log of 3 plus the, or I'm sorry, minus the log of 2. I get 17.6% of the data should start with a 2, and so on. Okay? So this guy developed that. Kind of cool. Anywhere else we find logs in the real world? Base 10 or base E or base, there's different bases. How's about my music people in here? Where's my music people? You gonna play music? Nobody here plays music? The octaves. Base 10. Anybody here in science class? Chemistry maybe? What's base 10? pH levels?
Oh yeah.
pH levels are base 10.
It's your S.
Earthquakes. Shell base 10.
That's like the highest.
Who's ever watched CSI?
Oh yeah.
NCIS? When the body's laying there, what's the first thing they ask?
Wow.
What's another thing they have to find out?
Um,
How long he's been laying there dead, right?
yeah.
How long has he been dead? Based on logs.
It is.
It is.
That is a law.
That is a log.
How is it?
Yes.
Wait, how does that work?
We're going to talk about it in a couple slides.
A couple slides?
A equals PE of the RT. So we already have this next day.
Tell me there's a bunch more.
We want to rewrite this in terms of RT. We want to get the RT by itself. Okay? We want to get the RT by itself. So what's the first thing we got to do?
Get rid of it.
Get rid of the P. So we're going to divide by P. And guys, I always like to have my base on the left, so I'm going to rewrite this so the E to the RT is on the left. Now, how can I rewrite that so the RT is a number? It is Kappa. Okay, how can I get RT down as a base number?
Take the log of it.
We can rewrite it as a log, because look, this is a B, this is the E, this is the N.
Bunny.
So if I do, what kind of log do I have to do though? I have base E, so the natural log. There's my B, which I don't need to write because it's base E, equals RT. So I've rewritten that in terms of RT, or as a function, right? So now, we're going to use that on the next slide. Let me copy it. So PERT is not, bodies do not decompose continuously, but we do make money compounding continuously. So how long will it take to double your money at 6.5% compounded continuously? So a question for you, Kate, with holes in her jeans.
Oh, I'm not gonna get this.
No, just give me the amount of money you want to deposit.
$300.
$300. Okay, so her starting amount is $300. She's a big investor.
Big investment.
What would her ending amount be if she's doubling her amount?
600.
So if I start with my formula, what is A over P going to equal? What's 600 over 300? 2. Do you think that relates to the word double?
Oh my god.
Oh my god, it's always going to be 2 when it's doubling, right?
That's always gonna be 2.
So you don't have to have a starting amount, is my point. So we're going to take the natural log of 2 equals the rate times t. And then how do you find your t?
You divide by
Divide it.
0.065.
Divide it, please. I would like y'all to use your calculators and make sure you're not making a mistake. Make sure you're using the right log.
30.76.
What is it?
30.
30 point. See, that's why I said please use your calculator so we can see if we're going to do this wrong. You need to make sure that when you pick your calculator up, when you type in natural log, it automatically starts a parenthesis. You have to close the parenthesis after the 2.
It's the natural log of 2.
So you got to make sure you close that
Where did I
parenthesis.
find that?
Okay?
I got it. That's 7.7.
Close parenthesis. So natural log of 2, close parenthesis, divided by.
Oh, we do the natural log first.
Yes. All right, here we go. At what rate of return? So now we're looking for the interest rate. Same idea. We're doubling our money.
Right.
If I said tripling, it would be natural log of 3. Doubling the money. Compounding continuously. What's your rate have to be in order to double your money in 5 years? Nope. Same idea. What'd you get?
0.138. 0.139.
So 13.8%?
Yeah.
Okay.
Oh yeah.
0.9. Thank you. I hate it when people round
Girl,
that
the
way.
holes in her jeans. She knows this.
Holes are making me think.
But there are no holes in my brain.
That's right. Here we go. Ooh, Newton's law of cooling. So, physics. 2 more slides. This is it. No more.
Oh, okay.
Newton's law of cooling. This is the formula you would use to figure out how long a body's been dead.
That's so sad.
But
like, how do you
when you said that?
Huh?
How do you
You
like
smiled way too
that?
much when you said that.
An object that has been heated will cool to the temperature of the medium in which it is placed, such as surrounding air or water. The temperature T of the object at time T, so that means the ending temperature, can be modeled by the function above. So the subscript M is the temperature of the medium, like the temperature of the air, or like if you put a boiled egg and you dip it in cold water, the temperature of the cold water. Okay. If you take a cake out of the oven, you set it on the counter, the temperature of the air is going to cool that cake. So that's the air, the temperature of the medium. The T sub 0 is the initial temperature of the object. Okay? So this is how the criminals get away with killing somebody, because like they turn the air conditioning on really high and they mess with the temperature of the room, and then they reset it. And the temperature of the room is not the medium that they think it is, and it affects the rate of cooling. Because I watch a lot of fractions.
Do you watch Criminal Minds?
I do.
Oh, I love that show. It's my favorite.
I could pass an easy psych just by watching it.
Have you seen Logical Sum yet?
I have.
It's my favorite show.
I've only seen the first one. Don't spoil
I like Barry
It's
more
pretty
than
good.
Betty.
it. Yeah, it looks good. Okay, moving on.
Please post it.
A local McDonald's franchise has discovered that when coffee is poured from a cup or a coffee maker whose contents are 180 degrees, so that's the, I'm sorry? So that's the initial 180, into a non-insulated pot after 1 minute, the coffee cools to 165. Okay, so we've got these first.
It's just the first part of the whole pair.
All right, but I want you to understand, we have to write a formula using that. But first, let's rewrite this formula so that the KT is by itself. So what's my first thing? We got to subtract T sub m, right? We got to get to the base. So how do we get rid of the parentheses, guys? We want to get the e by itself first.
Divide it.
Divide it. That cancels this guy, right?
Yeah.
So now we're back to Ben, the log bunny. So this is b to the e equals n. So we're going to do the natural log of t sub t minus t sub m over t sub o minus t sub m equals negative kt. And that will be good enough for what we need. Okay?
Could it just be natural log of t sub t over t sub o, because then tn will cancel?
Wouldn't that be nice if we could just cross those out?
We can't.
We cannot do that though, because you have minuses. So again, here, let me prove to you, because you guys don't believe me. Nobody believes me when I do this, but what does the top subtract to?
7.
And the bottom subtracts to 11. Does that equal 9 over 13?
No.
See how it doesn't equal?
The gas station.
Did you just put that in your calculator?
Yes.
They're both fractions. Scary. All right. Understand that's the reason why. You can't cancel if you have a plus or minus. All right. So using the numbers in that yellow deal, find me a rate of cooling. Here's our problem. We don't have the rate of cooling. And we're looking for, the actual question says, how long should we wait before pouring the coffee to deliver to customers? Okay, so we have to find the rate of cooling first. So natural log of, we want the temperature at the end of 1 minute to be 165, minus T sub m, the room temperature is 72, over T sub 0, the coffee when it comes out of the pot is 180, minus room temperature again. And the time is 1 minute. So what is my cooling rate? I'm going to put this in our calculator. Natural log of, I would like you all to pick your calculators up, because guaranteed half of you are going to mess this up. Okay, don't believe me.
I want a negative number.
I got an error.
Did you?
I got a negative number.
Hey, wait,
I actually got that.
you should get a negative number because it's a negative on that side, so they cancel.
Divided by negative 1. That was positive 0.1495.
Positive 0.1495. Now, you have to, guys, be very careful. Natural log, it automatically starts a parenthesis. You have to put this in parentheses and this in parentheses when you put it in. Or you can subtract, you're subtracting first and get a number. Right? 165 minus 72 is 93. And then over 108. So that would be the easiest way to do it. So that's your cooling rate, 0.1495. Now, we're going to do it again. But now we want the temperature to get down to 125. So it's going to be 125 minus 72 over 180 minus 72. So the only thing we're changing here is the ending temperature. And now we have the K and we're looking for the T. I get approximately 4.76 minutes. So I would say, to be safe, wait 5 minutes before you serve the coffee. If you don't wait 5 minutes, you're going to get too involved in the story.
Iced
Right? Okay?
We have that memorized for the test.
Oh, that would be a great thing to have memorized, wouldn't it? I think we would give you that.
Memorize it for the test.
All right.
That's a memory.